Welcome to this new session. In the last class, we discussed about the coordinate vectors. So this class we introduced the new topic is the linear transformation of a vector space. Actually, this linear transformation of a vector space you already studies the functions. So we start from the function and then we have to move to the linear transformation. So function means a function means you can say that a rule assigned that each element for one set to exact one element to the another set. When a unique element you can find into the set of a B. If we have a and B are the two sets, so the rule that assign a element of a x belongs to A, there is a unique element exists into the B also. This means we can say that f of x is equal to some y. X is the element of A. For every x belongs to A, there exists as some y from B. So another set into this. So this is the well known definition of a function. You already know that what is A is set. A is called the domain where it is the function start, and B is called the codomain where it's the function is end. Lengths you have it like this. I just show you by the figure. Actually, I just say that we have a this types of a figure. We have two sets are A and B are the two sets, and there is a some under rule, whatever rule we have to define is there, and the elements of this you have a like this. Suppose this x, and then we have a some image from finding there that is equal to y is equal to you have a fx. If we have a defined f of x is equal to y, and the element of this is called is you have a called is the domain. This set A is called is the domain, and this set B is called is the codomain. And also we just say that when for x assign this we have to just say that, and this y is called the that is y is the image of x under f. So whatever this you have to just say that these two maps is there. Suppose we have this is a y, this is, so this means this we can say that like this, y is the this is image of a f of x under a y. Whatever image of a this we have to finding into a this form, this is called the image. So what is the range or image? We can say the range of image of f is the set of actual outputs of the function proceeds. So range of f is nothing fx of a. This is the clearly this is the subset of a b is there. For domain, we just say that that is the this element. We can just say that this is our domain. We have to this set A is a domain, and this actually set is a B is our codomain, and that's parts we have to just when a range of f or image of f is nothing but is equal to this is the subset of this codomain where f of x is f set of all actual outputs of the function of the proceeds, means we have to finding all the values of our fx is this is image clearly is a range or image of a this in the case of a this function we have to define. That is a well known, you have to already know about the function is there. Now what we do for a linear transformation, actually this we have to taking is a two set. In place of a two sets, we try to take a two vector spaces. So if we take a vector space V and we have to vector space W, then we have to define a well defined map from V to W, and then it satisfies certain properties is a linearity, and it means like this we have to just say that any element y in place, suppose in place of a set A we have to take a vector space V, in place of a set B we take a vector space W, and then we have a this is the some point, this is you have a V, and this is somewhere you have a sub W, that this is a map where T over this means is mapping to this. So this means T of V is equal to you have a W like this function. But what this, because this is the vector space, that means this T preserve the under addition, and T also preserve the scalar multiplication. Because of a vector space, the this element of a B, because this set V is a vector space. If it is vector space is there, then you have a, if you have a U and V are two elements of a V, then clearly U plus V is also the element of a V, and then V. and also you have a, if you have a alpha is a some scalars are there, and u are the vector space of a V. This means we can say that alpha u is also the element of a V. So what with this we can say that is a linear transformation. That means this preserve the additivity. We have a suppose somewhere is a u also there. So means in the sum of these two vectors somewhere is equal to this is a u plus v. So we can find the image of a, because not a w. This means this find image. This is tw means this is equal to t of v, for example. So we can find a certain element where it is a reserved into this form. T of u plus v is also image from into this set vector space of w. That is called as the preserve the additivity. And also because this u is the element of a v alpha square, so somewhere we have a this element is a, you have a alpha u is also the element of a v, and this is a map is defined. So we have to also say that this where is somewhere is a t of alpha u. So also preserve the scalar multiplication. So that means we can say that the linear transformation is nothing but is equal to, in a function, so we have to generalization of a function. In function we have a two sets, but in place of a two sets, what we take? We take a two vector spaces, and function is a defined under this map. Images are there, but in linear transformations we have to linear means we have already linear t condition. We have to asking about this. So that means because of a vector space, all the elements belongs to the V. The sum is also belongs to V. Scalar multiplication also belongs to V. That's the reason we can just say that if the sum of these also preserve into W under T, this transformation, and then scalar multiplication is also preserved. If this satisfies these two conditions, then we can say that this map T from V to W is defined. Whatever defined is a linear transformation. If any one of the preservedness is does not satisfy, then we can say that this transformation is not a linear transformation. So proper definition is this: let V and W be a vector space over the same field. That is a condition we have to assuming this. V and W be defined on a over the same field. So we have to real number, so we have a real number. So a map T from V to W called a linear map or linear transformation. From V to W if the following two properties hold for a vectors V and W, and for every scalars of this. First is a T of U plus W is equal to T of U plus T of W. Why? Because this sum is under the addition into V, this sum on V, and this is the element of a W, and this is also the element of a W. So this sum, because we have to taking the W is a subspace, so this sum is also is a W. So this V and W are the element of a V. So this sum is defined. This sum is belongs to the V, because this is the V, this is the W. So this means this is the element of a V and W in V. So this means this is the element of a V, and this Tu is the element of a W. Tw is also the element of, because the element of sub V, this is mapped in the form of a T of V form. So this is the element, and this into this form. So that's why we can say that what we can T preserve the vector addition. Means over we have to know that U plus V plus W is equal to V plus W. So this means T over V plus W is the same as a T of V plus T of W. So we can say that this map preserved under the T is preserved under the addition. Similarly, V is the element of V, alpha is a scalar. This is the element of a, you have a V, and this is the scalar, and this is the element of a, you have a W. So this means whole thing is the element of a W. That means T preserve the scalar multiplication. So if a map, if we have a two vector spaces V and W over the same field, and we have a map from T to T from V to W is called as a linear map or linear transformation from V to W. If this satisfy these two conditions, means T preserve under addition, vector addition, and T preserve under the scalar multiplication. So now this is the same, but just so that we have to take it into this form by this. And now if we have to define a map T from V to V is called as a linear operator, simple thing. So if V is a vector space, the linear mapping or transformation T from V to V, then domain and codomain are the same vector space. If we take, then is called as a linear operator. In place of a linear transformation, we can just, if we have a any map from V to V, and that preserve the T preserved under vector addition and T preserved under the vector scalar multiplication, then we can say that this map is a linear operator in place of a linear transformation. We can just say that. Okay, so we just take a very trivial one of the two significant linear transformation. First one is U and V are the any two vector spaces, and V, the question is this is T from V to W such that T we define into the form of this. Then every element of a V. So is a linear transformation or not? So we take a check if this is a linear transformation. That means this should satisfy both the conditions of a T preserve under vector addition and T preserve vector scalar multiplication. So we take a any two V and V. We take a V1 and V2 are the element of a V, and by the definition T of V1 is equal to identity element of a this W, and we have a T of V2 is also the identity element of a W. Then what we saw that T should be preserved, then we can know that if V and these are vector spaces, so we have a V1 V2 is the element of a V, so this means V1 plus V2 is also the element of a V. And if also the element of a V, this means this can say that by the definition this can be written as a T of V1 plus T of V2. And now by the this is again by the definition, this is again element of a V. T of V is equal to T 0 of a W. And now if we take a T of V1 is equal to 0 of a W, and then you have a sorry, this we can write take a sum of these two. So we just write a T of V1 plus T of V2. This can be written as a 0 W plus identity of W. And now by the property of a vector space, because W is a vector space, so this can be written as any element which is written the identity element gives the identity element. So this is giving you a T of W, and this is also giving a T of W. That this implies that we have a T of V1 plus V2 is equal to you have a T of a V1 plus T of V2. Now we have also you have a V1 is the element of a V, and then alpha is the element of a R. Then this implies that because V is a vector space, we can say that alpha V1 is also the element of a V. And then because it's the element of a V, again by the definition of this T of alpha V1 is nothing but is equal to identity matrix of additive identity of a W, and we have to calculate T of alpha of a V, and then alpha times 0 into W. T of V is given to this form, and now we know that the property of a vector space alpha dot this is again is a identity element of this same set. So this means alpha V and this again the same set. So we can say that T of alpha V1 is the same as the alpha times T of V1. So this means this map clearly preserve the under vector T preserve under the vector addition here, and also T preserve the vector scalar multiplication by there. So this satisfies both the condition of a linearity. That means is a map define TV from as V to this. Actually, this map of this types is this. You can say that this is a U V, and this is a you have a W, and this is a you have a W. Here is a identity element of this W, and we say that T of V for every V, so it means all the V is there. So this means this is mapping to whole the V is mapping into this form in this form. We have this all the element is mapping into a identity element, this collection of this way. So this means such a map is called we can call is a zero transformation. So this means every element is mapped to the zero. So this transformation is called is a zero transformation. So this is a clearly is a linear. By how we have to prove that, and then clearly we have to show that this is a zero transformation. Now another transformation we define the form of a T of V is equal to V. Now what we just said is again we have to take is the both the condition is satisfy or not. V1 V2 belongs to V. This implies that we have a V1 plus V2 is also the element of a this, and alpha is the element of a R. and this implies that alpha times V1 is also the element of a V. So by the map defined, we can say that T of V1 plus V2 can be written as the same as a V1 plus V2, and by the because these two elements are V1 V1 V2 belongs to the V, so this means clearly T of V1 is equal to V1, T of V2 is equal to V2, and also we can just say that T of alpha V1 is equal to alpha times of a V1, like this. By the this, because this is a V1, so this can be into this form. Or simply this T V1 V2 belongs to the V, so T of V1 plus V2 is equal to V1 plus V2, but V1 is equal to, we have a T of V1, V2 is equal to, we have a T of V2. That means this is preserved under addition, and then we have a also T alpha of V 1 is equal to alpha times of a V1, and this is nothing but alpha times of a V1. V1 is equal to, you have a T of a V1. So this also preserved under the vector scalar multiplications. So vector addition and also vector scalar multiplication. So that means we can say that this is also is a linear map, and this linear map is called as a identity operator, because this is defined from V to V. So we can say that identity operator, you can also say as a linear map, identity map or identity linear transformation. This is not a because we have a V is a, but in generally when we have a domain and codomain is the same, we can say this is a operator. Okay, so now this is the trivial linear transformation. So we just try to some other different types of a linear transformation. So we take a V is equal to R2. I take again, this is a from V to V is a linear operator. So we have a map is defined into this form, and now we check is this is a linear map or not. So we just first we take two different elements. So we take a V1 is equal to form of a we take a we take a V and U and V. U is the element of a, we have taken upon U1 U2, and V we have to take is a V1 V2, and these two are the elements of a V. And then we take what is the U plus V. U plus V is nothing but is equal to U1 U2 plus V1 V2, and by the component wise addition we can say that U1 plus V1, and then we have a U2 plus V2. So we just say that define, we just calculate what is our scalar multiplication. So just before this we just take a scalar multiplication. How defined a scalar multiplication? So alpha U is equal to, just write as the form of alpha times of a U1 U2. This is alpha times of a U1 and alpha times of a U2. Now we take a U plus V. T of U plus V can be written as T of U1 plus V1, and then you have a U2 plus V2, and then this map is defined in the form of this V1 minus 2 V2. So this is V1, this is your V2. So this is defined in the form of a U1 plus V1 minus V2. So you have a U2 minus V2, and then you have a U1 plus V1 plus 2 times of, you have a U2 plus 2 times of a V2. And now we just take into this form, we take a U1 minus U2, and then we have to write a plus, sorry, we take a minus. Okay, so plus you have a V1 minus V2, and also we have to write is a U1 plus U1 plus twice U2, and then we have to just say that plus V1 plus twice of a V2, and then this can be written in this form. And now this can be written in the form of a U1 minus U2 comma U1 plus twice U2, and then we have to write plus we have a V1 minus V2, and then we have a V1 plus twice V2. And now you see this is nothing but is equal to by the definition, this can be written in the form of a T of U, and this is written as a form of T of V. That means this T is preserved under the addition, vector addition. So this first condition is satisfied. So now we have to check the another. So this means we have to just say that is satisfied clearly. And now we try to find the another condition. So we have to take t of alpha times of a u, t of you have a alpha of a u1, alpha of a u2, and by the definition this can be written as a you have a alpha times of a u1 minus alpha times of a u2, and then you have a similarly you have to just say that alpha times of a u1 plus 2 times of alpha of u2, and because this can be written in the form of alpha times of a u1 minus u2, and this can be written alpha times by the distributive property u2 u1 plus 2 times of a u2, and now again by the definition of this scalar multiplication of a v, this can be written as a alpha u times u1 minus u2, and then you have this is u1 plus twice u2, and this is nothing but is equal to alpha times of you have a this is value is you have a t of u. So this means this map also preserve under the vector scalar multiplication. So this satisfy both the conditions. So this means t is our given map is a linear transformation is this thing. Okay, so now I think this is clear how to calculate the linear transform. I try to some more examples. We define a map into this form. I just check from R2, we have to take a R2 to R2, but I take this is a linear transformation from R3 to R2. So this means we have to take two elements u and v are the element of a R3. So this means V is a R3. So you can be written as a suppose U1, U2, U3, and V can be written as a V1, V2, V3. We calculate U plus V, and by the definition this can be U1 plus V1, U2 plus V2, and U3 plus V3. Also alpha U can be written as alpha times U1, alpha times U2, alpha times U3. Now we calculate T of U plus V is equal to T times of U1 plus V1 and U2 plus V2, and you have a U3 plus V3, and this map is defined to this U V1 minus V1 minus V2. So this can be written in the form T of this can be written in the form this is you have a U1 plus V1 minus V2. So you have a U2 minus V2, and then you have a U1 plus V1 plus U3 plus V3, and this can be we combine into this U1 minus U2 plus we can write in this form V1 minus V3, and this can be also written as a U1 plus U3 and plus V1 plus V3, and that means we can just say that this can be written in the form of a we have a like this. So this can be written in the form of a u1 minus u2, and then you have a u1 plus u3 plus v1 minus v3, and then we have a v1 plus v3, and this is nothing but is equal to you have a t of u. Sorry, this is no need. This is nothing but is equal to you have a t of u, and this is nothing but is equal to you have a t of v, because you have a v is equal to v1 this is equal to v1 comma this is v1 comma v3, and this is v1 comma minus v2 and v1 plus u1 v2 and so on. So this means this is preserved under the vector is addition. Now we have to check is this vector a scalar multiplication. So we take a t of alpha of u is equal to t of we have a alpha u1, alpha u2, alpha u3, and this means again by the property we can say that alpha u1 minus alpha u2, alpha u1 plus alpha u3, and this can be written as alpha times u1 minus u2 and alpha times u1 plus we have to just say that is equal to you have a u3, and this is nothing but is equal to again distributive property alpha times of a u1 minus u2 and u1 plus u3, and this is nothing but is equal to alpha times of a t of a u. So this means this again preserve the under scalar multiplication. So this map T from R3 to R2 preserve the under the vector addition and also under the scalar multiplication. So by the definition, this again map is satisfy both the condition of a linearity, and so if we satisfy both the condition of a linearity, means we can say that defined map is a linear map is there. So okay, now we have to just reverse this order, and now we take a T from R2 to R3. Now we have a element is like this. We have an image for a R3. I just take a previously I defined from R3 to R2. Now I take a R2 to R3 is this form. So again we take a U and V are the element of a R2. So U is the form of a U1, U2, and V is the form of a V1, V2, and then we take again U plus V is the form of a, you have a U1 plus V1 and U2 plus V2. Now we take a T of U plus V is the form of a T of U1 plus V1, and then you have a U2 plus V2, and then V1 plus V2. So this means this plus this. So you have a U1 plus V1 plus U2 plus V2, and now next term is you have a U1 plus V1 minus you have a U2 minus V2, and then the last term you have a U2 plus V2, and this can be rearranging again the U1 plus this is we have a this is you have a 2, so this is 2, so U1 plus U2, and then we have a plus V1 plus V2, and then you have a U1 minus U2 and plus V1 minus V2, and then this is a U2 plus V2 as it is. Now this can be written in the form of a U1 plus U2, and then you have a U1 minus U2, and then you have a U2 plus, similarly we can write is a V1 plus V2, V1 minus V2, and this is equal to V2. So this is nothing again by the definition of this. So T of I can just say T of U is nothing but is equal to, you have a U1 plus U2, U1 minus U2, and you have a U2, and then so sorry, this is all is U2, U2, and this is nothing but is equal to, you have a T of U, and this is nothing but is equal to, you have a T of V. So this means we can say that this this is again you have a T of V. So this map preserve the under addition. Now we try to check is this map is preserve under scalar multiplication or not. So we take a because alpha of U can be written as alpha times of a U1 alpha times of a U2. So we calculate T alpha U is equal to, we have a T of we just take a this thing alpha of U1 alpha of U2, and by the definition this can be written in the form of alpha U1 plus alpha U2, and then we have a alpha U1 minus alpha U2 and alpha U2 again by the scalar multiplication property. This can be written as alpha times U1 plus U2, and we have alpha times U1 minus U2 and alpha times U2, and then again we can just check by this distributive property, this come outside alpha times of a U1 plus U2, and we have a U1 minus U2 and you have a U2, and this is nothing but is equal to alpha times of a T of U. So this means we can say that clearly this satisfy the all the two conditions of the linearity. So that means we can just say that T preserve under the vector addition, and also T preserve under the vector scalar multiplication. So both the condition of a linear transformation is hold here. So now we have to discuss this three different types of examples and two standard linear transformation today. So I stop here. In the next class we have to continue some more examples of a linear transformations, and we discuss the property of some linear transformation into the next session. Okay, thank you very much for this session.